In Chapter 2, we're going to focus on atoms and elements. As always, there's suggested problems for you to work on at the end of the chapter. These will help you to know if you understand the concepts. Atoms are so tiny that we cannot see them using a light microscope, but we do have ways that we can observe their presence. We can use a scanning tunneling microscope. And so in 1981, it was found that if you pass a very sharp tip over a flat metal surface, that current that flows between them, it changes depending on how far that tip is from the surface. And so by doing this and moving across in a very organized fashion, we can see the atoms on the surface. So that current that passes is what we call a tunneling current. And this allows us to take pictures of atoms. So if you notice the scale on our picture, we are in nanometers, and we're at a very small scale between 0 and 2 nanometers in this distance. So atoms are very tiny. Now we took it a little bit further with the scanning tunneling microscope and got to the point where we could actually pick atoms up, move them around, and set them back down on the surface. And so I'm told that this particular image says the word atom. Now, using this technique, there's a video or a movie that was made called A Boy and His Atom. If you would like to see the world's smallest movie, I encourage you to look up A Boy and His Atom, made by IBM. In the past, scientists could not use a scanning tunneling microscope. They had to use other ways to determine that there was the presence of atoms. In the 1700s, Antoine Lavoisier determined that there was a law of conservation of mass. This says that in a chemical reaction, matter is not created or destroyed. The way that he went about this experiment was carefully measuring the mass of the reactants prior to a chemical reaction, very carefully collecting all of the products that were formed, and he found that no matter which chemical reaction he was doing, those masses were equal to each other. Before we start talking about atoms, we're going to have to keep in mind some things about charge. So remember that when we have opposite charges, when we have positive and negative charges, those are going to attract each other. If we have the same charges, so two positives, they're going to repel each other. Two negatives are also going to repel each other. And in order for something to be neutral, it has to have an equal amount of positive charge as negative charge. So those amounts have to be equal in order to be neutral. We're going to keep this in mind as we talk more about the subatomic particles. We're going to very briefly talk about the history of an atom. If you are very interested by this history, your book has more detail. Dalton first proposed the idea of an atom following experimentation, where he found that different compounds combined in a certain fixed ratio. And this was called the law of multiple proportions. J.J. Thomson discovered electrons, and he proposed the plum pudding model of the atom, which he said there was a positive charge, and inside that positive charge there were these negative electrons that just kind of were in there. Another way to think about it is maybe a blueberry muffin model of the atom. Rutherford discovered the proton, and he proposed the nuclear model of the atom. So the positive charge is in the center of the atom, and it's surrounded by a lot of empty space where the electrons are. So we have three subatomic particles. We have a proton, which has a relative mass of about 1 AMU, which stands for atomic mass unit. We have electrons, which are negatively charged, and they have a much smaller mass than a proton, almost small enough that it becomes not significant to the mass of our atoms. We have neutrons, which are about 1 atomic mass unit. Our protons and neutrons are found in the nucleus. The electrons are in the empty space around it, which is why when you see atoms, you typically see them drawn something like this. So our electrons are orbiting our nucleus, and we have positively charged protons and neutral neutrons. Our symbols for a proton are either P, P+, or H+. So why would we have H+ as a symbol for a proton? Well, if we think about it, hydrogen has 1 proton and 1 electron. And if we remove that electron, it just becomes a proton. And that is why it gets represented as H+ for a proton. Electrons typically are E-, and I use this notation very frequently. And neutrons are either N or N with a 0, representing that there is no charge. Elements have a unique number of protons in the nucleus. So if we're going to change elements, we change the number of protons. The number of protons that are found in the nucleus, that is what we call the atomic number. And on our periodic table, that is the number that's normally found in the upper part of the box the elements are labeled in. They are also arranged on the periodic table in order of increasing atomic number. Each element has a unique name and symbol, and the symbol is a capital letter, and if it has 2 letters, the first one's always capital, the second one is always lowercase. And we'll talk about why that is in a little while. So if we change the number of protons, we change the element, and that also changes the properties. So helium, which is a gas at room temperature that is lighter than air, has 2 protons. Carbon, which is a solid at room temperature, has 6 protons in its nucleus. So by changing the number of protons, we change the element and also its properties. On our periodic table, our atomic number that tells us the number of protons is found at the top of the box on our periodic table. The chemical symbol, which is 1 or 2 letters, is found in the middle. Not all periodic tables include the name, but some of them do. When we look at our periodic table, that atomic number tells us not only the number of protons, but also the number of electrons if we have a neutral element. Because in order to be neutral, we have to have equal positive and negative charge. Some symbols are 1 capital letter, like carbon or sulfur or iodine. Other elements have two letters, and they are always uppercase for the first, lowercase for the other. The reason for this is because CO is different from CO. So CO is cobalt. CO is carbon monoxide. So we do have to be very careful with our capitalization. Some of the element names make sense, like C is for carbon, S is for sulfur, H is for hydrogen. Others come from the Latin name because they were found a very long time ago. So they were named in Latin, like OU is gold, CU is copper. Whoever discovers the element gets to the rights to name it. So we also have some like berkelium and americonium and germanium that are named because of the people that discovered them. Einsteinium. Protons and electrons are not the full story when it comes to atoms. We also have neutrons, and by adding neutrons, that changes the mass of our atom. That leads to isotopes. So when we talk about our isotopes, we write something called an isotopic symbol or an atomic symbol. We represent the elemental symbol. We put the mass number at the top, and we put the atomic number at the bottom. This helps us identify different isotopes. Isotopes chemically behave identically. They are found in different abundances. So carbon has carbon 12, carbon 13, and carbon 14. Six. And these are different isotopes. They are found in different abundances in nature. Carbon 12 has the highest amount of abundance. Carbon 14 has a very small abundance. Carbon 14 is radioactive, and it decays at a very predictable rate. And so we can use the amount of carbon 14 in a sample that was previously living to help identify how old it is. And that's how carbon dating works. So if we look at neon, neon has 3 isotopes here. You'll notice that we're writing them using our atomic symbol, or we are just putting a dash with our mass number. Either way is acceptable. So if we want to find the atomic number is the one that is on the bottom of our symbol, and because these are all isotopes of neon, we have the same atomic number, same number of protons for each of our rows. If we look at the number, our mass number, the mass number is written on top, and we have different mass numbers for our isotopes. That mass number helps us to determine the number of neutrons, because protons plus neutrons equals our mass number. So in order to find the neutrons, we take our mass number, subtract the protons, and we can find our neutrons. And again, these have different abundances found in nature. Let's find out how many protons, electrons, or neutrons are in an atom of chromium-52. So we are given our atomic symbol. We can find our number of protons. So protons, again, are given with the atomic number. Because it's neutral, there's no charge written, so our electrons are going to be equal. And our neutrons we can find by taking the mass number minus our atomic number. So in this case, 52 minus 24. We get 28 neutrons. Pause the video and see if you can complete this table. So remember, atomic number is equal to the number of protons. Mass number is the protons plus the neutrons. The electrons are going to be equal to the protons because the element is neutral. And we write our atomic symbol with the mass number on top, the atomic number on the bottom, and our elemental symbol. We can look at the number of protons and a periodic table in order to come up with our elemental symbols.